cylindrical and spherical coordinates. The neat thing about the algebra and the trigonometry, how it relates to the calculus, is that there's maybe about a handful of trig terms that you need to carry you all the way through, whether it's calculus 1, calculus 2, calculus 3. I share with you a couple of those neat facets of trigonometry, and it's what I use, and it helps out a whole lot. Okay, so I think the first thing that you want to recall from trigonometry is how to build the relationships between the 30, 60, and 90-degree angles. So what we'll do is we'll take an equilateral triangle and for the sake of simplicity, we'll set each side equal to 2. I'm choosing 2 because I need to bisect one of the angles, and in bisecting an angle, I'm going to also bisect the line segment that's opposite of it. So I'm going to bisect this angle, and so this side is 1, that's 1. If it's an equilateral triangle, that means that all the angles are equal to 60 degrees. So here, this is 60 degrees. Now when I bisect that guy, then I get 30 degrees in there. $60 degrees or power of 3 power of 6. If I just take one of those triangles out and just examine that, this is 1, this side is 2. If I use the Pythagorean theorem, then I get, from solving this leg, I get the square root of 3. Does everybody agree with me on that? Okay. Just using the Pythagorean theorem, we get the square root of 3. Now from this triangle, you can build all of the relationships that you want in terms of the 30 and 60 degrees. So if we look at cosine pi over 3, get 1/2, sine pi over 3, the square root of 3 over 2, tangent of pi over 3 is the square root of 3 over 1, or just the square root of 3. You can flip them and get the cosecants and the cotangents and secants and that type thing as well. Also, if we look at cosine of pi over 6, that gives us the square root of 3 over 2. Sine of pi over 6, 1/2. Tangent pi over 6, get 1 over the square root of 3. That's the first thing that I think is very useful in gleaning from trigonometry. The second thing is the relationship with the 45, 90 degree angle. So let's call that number 2, and then we'll move on. Here, if I take a square, and let's fix all sides to be 1, bisect one of those angles, and so in doing that, if I just pull one of these guys out, one of these triangles out, this is 1, this is 1, that angle there is 45 degrees or pi over 4. if I use the Pythagorean theorem, I get the square root of 2 for this side here. And so from there, I have all the neat trig terms that I need. Cosine of power over 4 is 1 over the square root of 2, or if you want to write that as the square root of 2 over 2. Sine of power over 4, 1 over the square root of 2. And then the tangent of power over 4 just equal to 1. So those are helpful, and as we work some of these problems, we'll refer back to these two just to help us out. And you know, I know a lot of you've kind of memorized the unit circle, and that's good. And then some you just use your calculator. I mean, that's cool too. The unit circle for me when I was a kid in school, it was just too much stuff going on. And so, yeah, it's a lot going on. So I tried to simplify it by just using this information right here. So let's see, as we move on, we talked about here x equal to r cosine theta for the cylindrical coordinates, y equal to r sine theta. Tangent theta is y over x. All right, thank you, Donnie. And then r squared equal to x squared plus y squared, just right from the Pythagorean theorem. And so we have that. Second thing I want to do is to talk about the spherical coordinates, and then we'll work some problems for this section. Okay. So for the spherical coordinates, I still want to relate the point P, which has coordinates x, y, z, but here we relate them to some directed distance in space that we call rho. Theta is the angle in the xy plane, and then here phi becomes the angle out in space. There's a strict requirement for phi, that phi is on the this interval from 0 to pi. So basically he goes from 0 to power over 2 to pi. He doesn't go all around. Now to get the all around nature, what they do is to either negate rho, and if you negate rho, then you jump downstairs, and then you measure again from 0 to pi. But this guy is defined on this interval right here, and so that's important. I think that's about the only thing that stands out that looks to be a little odd. Theta back for the cylindrical coordinates is defined from 0 to 2 pi, but here phi is defined from 0 to pi. So. Now let's see how do we pick up these values for x, y, and z for the spherical coordinates. I'm going to take this graph right here and see if I can put the interpretations to it. So if I have some angle here, we call that theta. This is x. This is y. This is r. Now when I jump up in the space, here's the point P, and P consists of, whether you say X, Y, Z, or if you say R, theta, Z, talking about the same thing, or here now for this new coordinate, for spherical coordinates, talk about rho, theta, phi. Now where are they? Here, if I measure P from the origin out in space, then this line here becomes rho. This angle is phi, this is Z. Now this line here is parallel to that. We form these parallelograms, so this is also R. Now what I'm going to do is take this triangle here that's embedded in there, let's pull it out. So we can just look at that by itself, so it kind of makes sense, so it don't look all too cumbersome. So if we pull that guy out, so here I have phi. This is rho. That's R. This is Z. Z is next to it. See? This is R over here. Good. So now let's write cosine, sine, and also tangent of this phi angle. So we get cosine of phi. So this guy is Z over rho. Now that implies then that I can go directly from the rectangular value of Z right to its spherical value, and that becomes rho times cosine phi. Sine of rho is equal to R, sine of phi, excuse me, is equal to R over rho. That implies here that R is equal to rho sine phi. This is important. This is important. And for the tangent of phi, this is here, the R over Z. Now, what I want to do also, you recall that x squared plus y squared is equal to r squared. But now that you're out in the space and you have this sphere, well, you directly get the equation of the sphere, and that is that x squared plus y squared plus z squared is equal to rho squared. Rho becomes the radius out in space. When I want to get this angle phi by itself, I'm going to use the cosine. And the reason that we're going to use cosine is because z is already in the rectangular coordinate, and then I can express this rho as the square root of x squared plus y squared plus z squared. See that rho is equal to the square root of x squared plus y squared plus z squared. So here we take cosine phi, which is equal to here this z over phi. And this implies that cosine phi is equal to z over the square root of x squared plus y squared plus z squared. And that implies just the angle itself, that phi is equal to cosine inverse of rho here, excuse me, the angle becomes the term cosine inverse of z all over the square root of x squared plus y squared plus z squared. So what I've tried to do was to try to derive from the graph all of those trigonometric forms that you need to be able to relate from rectangular to spherical to cylindrical in any given combination. Oh, by the way, now you know that x is equal to r cosine theta, right? But the r is not in the spherical coordinate system. Theta is, but r is not. So I need to be able to write r with its spherical equivalents. We use this. Best to use that. R is equal to rho sine phi. So this means that x is equal to, that r becomes rho sine phi times cosine theta. Likewise, y is equal to r sine theta. So y becomes, r is rho sine phi times sine theta. I think we have all the equivalents now. Now the author gives that to you, all that information there, right? But it's better, I think, when you see it directly from that right triangle, and you can glean from that, you know, what he's getting. Just feels better when you put your own hands on it. If you fishing, you want to catch that fish and you want to grab him, you know, once you put him out that water, he's in your hands. You know what I'm saying? Hey, man, you did something, you know. You go to a restaurant and you eating some fish, I mean, that's cool, but it just feels a whole lot better you out there, you catching that fish, man. You catching that bass, you know, that crappie, and you pull that sucker in, you clean them, you know, you get that grease ready. Oh, man, you know, it's, you know, either you want the restaurant fish, which is all this stuff right here, or you just want to catch it yourself. Well, that's a good analogy. Let's move on. Boy, I'm getting happy with my own crazy self. So let's see. First problem, convert the point. What we're going to do with the exercises here is try to go back and forth. If a point is given in rectangular, can you convert that to cylindrical or spherical or vice versa, any combination. So here, convert the point from cylindrical coordinates to rectangular coordinates. So it's in cylindrical, so let's label what we have. So if it's in cylindrical, you remember that guy has the form, this is r theta z. And you want to go to rectangular, that is, you want to go to x, y, and z. The neat thing is that z is fixed for both of them. So you look at that directly, and z is equal to 1. We got that part finished. So now it says that r is equal to 3, and theta is pi over 4. Well, since we know that x is equal to r cosine theta, I think we can get it. So x is equal to 3 times cosine of pi over 4. We just had the cosine pi over 4. That's just 1 over the square root of 2. So x is equal to 3 times 1 over the square root of 2. And it doesn't matter how you simplify it. I just say 3 over the square root of 2. Yes, sir. No. No. Yes, sir. So here, y is equal to r sine theta. So y is equal to 3 sine of pi over 4. On my test, you can't use a graphing calculator, but you can use a scientific calculator. You just type that on your calculator if you don't. Now, I just gave you a few pages back how I produce all the equivalents for the pi over 4, whether it's sine, cosine, tangent. So, and so I gave you that for a reason, because I knew that these things would come up. So this is y is equal to 3 times 1 over the square root of 2, 3 over the square root of 2, or you could say 3 times the square root of 2 all over 2, doesn't matter. So it asks for the rectangular point, so it's going to be 3 over the square root of 2 for x, comma y, 3 over the square root of 2, and then z stays the same for both of them. I don't know why on this computer these things tend to just move like a ghost sometimes. I had that issue last semester, and it didn't make me feel good. So anyway, any questions there? Let's look at another one. Convert the point from rectangular coordinates to cylindrical coordinates. So that means that here x is 2, y is -2, and z is -4. Well, if I have that, then I know that r squared is equal to x squared plus y squared. So r squared is equal to the 2 squared plus the -2 squared. So we just get 4 plus 4, we get 8. And so r is equal to 2 times the square root of 2. Boy, I'm losing my voice. So we have r. So for cylindrical, we need r, we need theta, and we already have z. Z is equal to -4. So now we solve for theta. So to solve for theta for cylindrical, we use the tangent, right? And to be honest, you can use cosine or sine. It doesn't matter which one you use to get it. It's good. You'll get the same thing. So say, for example, let's say if I was going to use the cosine theta is equal to x over r. So here, since I have r, I'm good to go there. So x is the 2 all over 2 times the square root of 2. Just get 1 over the square root of 2. Now, I'm thinking power over 4, but I got some negatives running over there with that y and that z, right? So just want to be very careful about that I get the right angle. Look at this. Sine theta is that -2 over 2 times the square root of 2. That's -1 over the square root of 2. So we look to see where's cosine, or where x is positive and y is negative. Which quadrant? Fourth quadrant, right? Yeah, the fourth quadrant, right, is where we are. So that's the key. So we're here. And if that be the case, you take the reference angle. The reference angle would be pi over 4. So here, if you're in the fourth quadrant, it's 2 pi minus the reference angle to get the angle that we need. So here, to get the angle theta, it's 2 pi minus the reference angle if we're in the fourth quadrant, right? So here, theta is 2 pi minus pi over 4, so we get 7 pi over 4. Okay. If I had used tangent, I wouldn't have had to gone through and looked at cosine and sine. So it all would have been right there in tangent, because tangent is going to involve x and y. Right? So it'll involve the sine for x, the sine for y. It's right there automatically. We get the same result. So r is 2 times the square root of 2. Theta is 7 pi over 4. And then z is negative 4. So you've gone from rectangular to cylindrical. Yes, sir. I'm going to write this a little bit lower down. Oh boy, what did I have here? Theta is equal to, yes, sir, 2 times the square root of 2, 7 pi over 4, and then negative 4. Yes, sir. Yes. Because I just wanted to show you that. Yeah. My instructions earlier were to use tangent. I didn't do that. All right, so tangent theta is equal to y over x. It's negative 2 over 2. We get negative 1. And so here, when is tangent equal to negative 1? Right. Now you can do this. Tangent is equal to, well, theta is equal to tangent inverse of negative 1. It'll spit out 7 pi over 4, or it'll say negative pi over 4. It's the same thing. Right? So this implies that you'll still go through the same argument, that the reference angle is pi over 4. And then now the question is, when is tangent negative? So when is the combination of x and y is negative? So you're either in the second quadrant or the fourth quadrant. But then how do you nail it down? What's the value for x? What's the value for y? X was positive, I believe, right? X is positive, y is negative. So x positive, y negative, you hammer that, you're right there in the fourth quadrant. So the reference angle is pi over 4. I'm in the fourth quadrant. Still, again, 2 pi minus pi over 4. You still get 7 pi over 4. Yes, sir. Thank you. Good question. Okay. I don't think there was another problem down there. Nope. Good deal. All right. In this exercise, find an equation in cylindrical coordinates for the surface represented by the rectangular equation. Now, I'm going to do the first one. All right. So, because it's very easy. They give me an equation in rectangular coordinate system. I need to convert that rectangular equation to cylindrical. So here, this equation in cylindrical is z equal to 4. because Z is in both quadrants. Z is also, it's in rectangular, is also in cylindrical. So I'm done. Told you that was the easy one. You do number 16. So what's an equation? If you go into cylindrical, that means that you don't have X and Y anymore. You got to have something. It could be R. It could be a combination of R and theta, or it can just be theta. But definitely no X, no Y. You can have Z. What's that formula for X going from X to cylindrical or polar coordinates? X is equal to what? R cosine theta. So if X is 9, that's just 9 equal to R cosine theta. You're done. Right? You know that X is equal to R cosine theta. Here it's saying X is equal to 9. So this is 9 is equal to R. That's it. All right. So for the next one, help me out. So I get X squared plus Y squared. So what should I write instead? R squared. So we'll say R squared minus 2Z squared equal to 5. That's it. Cylindrical can involve R and Z. I'm done. Okay, you do 19. Let's see what you get for that one. That's a good one. And then you simplify it. So let's see. So we have R sine theta is equal to r squared cosine squared theta. You can divide through by an r, so divide out one r if you want, and then you can divide through by that cosine squared theta, and so you have sine theta over cosine theta times 1 over cosine theta is equal to r. So that's tangent theta times secant theta is equal to r. Now, you could have written it like that, or you could have had 1 equal to r times cotangent theta times cosecant theta, and that would have been fine as well, too. Right? So, any questions there? Here, write the equation in cylindrical form. Write the equation in cylindrical form. So this y squared becomes r squared sine squared theta. If you want to put the plus z squared there equal to 10, or you could have left the z squared on the other side, but that's it. Cylindrical involves r and theta and also z. So it's just one stroke. Just convert the y squared to r squared sine squared theta. Basically, that's it. Yes, sir. Yeah, that's it, man. I think if you go any further, you get into some trouble. Because where else would you go with that? Yeah, you could do that and then take the square root of everything. Yeah, you could do that. But I'll just leave it like that. Yeah, yes, sir. Taking that square root, once you do that, then you run the risk of looking at plus and minus values as well. You know, the plus or minus the square root, you know, of something like that. So with this answer, this involves all solutions. Right? And we don't truncate anything off. Okay. Find an equation in rectangular coordinates and sketch the graph. So if I'm given r equal to 3, if I square that, I get r squared equal to 9. And so you know that x squared plus y squared equal to r squared. So here, since x squared plus y squared equals to r squared, this implies that x squared plus y squared is equal to 9. So my question now to you is, what is this? It's a cylinder. It's more than a circle. Yeah. If we're in the two space, it's a circle. But when they say the phrase cylindrical, well, it's given to be in cylindrical. And my statement here, I paraphrase what he had in the book, but he had, you know, given an equation in cylindrical coordinates. I skipped all that. I just said, find an equation in rectangular coordinates and sketch the graph. So anyway, the original phrase was that you're given an equation in cylindrical. That means that you're in the three space. From the 3 space, then if I have something like this, I don't think a circle. I think now a cylinder. So it's a cylinder with radius 3. Yes, sir. No, it's 3. The radius is 3. Yes, sir. Directly. No, you're fine. You're fine. So here, That's better. So I have this radius of 3. I told you I get in trouble when I do these slash marks. Oh, thank you. So you get this radius of 3. Since it's a cylinder, we're missing z, so it has rulings parallel to the z-axis. Isn't that a daisy? Well, it's a crooked daisy, but okay. All right, let's keep on pushing. There's no questions there. Find an equation in rectangular coordinates and sketch this graph. So here I'm going to directly look at the tangent of pi over 6. The tangent is said to be y over x. We have the pi over 6. I'm going to go back to my 30, 60, 90. So this was 60 degrees, or pi over 3. Up here was 30 degrees, or pi over 6. This side was 1, 2, square root of 3. So the tangent of pi over 6 is 1 over the square root of 3. 1 over the square root of 3 is equal to y over x. Now from there, just get y by itself, write this as an equation. So I get y is equal to the square root of 3 times x. In the 2 space, this guy is just a straight line. And the 3 space is a plane. Right? So we can plot a couple of points if you want. X is 0, y is 0. X is the square root of 3, y is 3. X is 1, y is the square root of 3. I think what I'm going to do is basically just, I think it's easier to graph this in x, y, and then draw the plane from there instead of trying to look at x, y, z and then graph the plane. If I did that, you won't see it the way it ought to be really seen. I've tried it before. So let's do this. We'll graph this in x and y. And then from there, we can draw the rulings with respect to z. So the origin, and then the square root of 3. The square root of 3 is like 1 point something, right? So it's a little bit more than 1. So let's say this is 1 there. So we get, I've got to go up a little bit further. 2 and 3. A little bit more than 1, and then 3 here. So the plane is a sheet that runs with this guy. So wherever that line is, that sheet of paper runs right along with it, right? So any questions there? This is a plane. Find an equation of rectangular coordinates and sketch its graph. R squared is x squared plus y squared. So this is x squared plus y squared plus z squared is equal to 5. So what is that? A sphere with radius square root of 5. So it's just a ball. Find an equation. Yes, sir. Go back. Yes, sir. Yeah, if I go a little fast, you got to slow me down like the old mule. Um, I heard Dr. Scruggs say on Pastor First Missionary Baptist in Huntsville, he says on his broadcast Sunday evenings that they had an old mule named Blue. and old Blue get beside himself. They got to say, "Oh, mule." So look, you got to call me in. Say, "Oh, say, hey." Yes. Yeah, man. Yeah, man. We have good church. We gotta get them. Gotta get them crunk, man. Y'all wake up. All right. Can I move on now? Okay. So find an equation of rectangular coordinates and sketch this graph. So if r is equal to 4 times sine theta, I'm thinking y equal to r sine theta. Because I see a r, I see a sine theta, right? So I'm going to come over here and just write that equation. Y is equal to r sine theta. I'm going to represent either the r by itself or represent the sine theta by itself. I'm going to get sine theta. Doesn't matter which one you do. So sine theta is equal to y over r. I'm going to use that, replace this sine theta over here with y over r. So I have r is equal to 4 times y all over r. Multiply both sides by r, so I get r squared is equal to 4y. But r squared is x squared plus y squared. So this is x squared plus y squared is equal to 4y. Subtract 4y on both sides, so I get x squared plus y squared minus 4y is equal to 0. It's some type of cylinder, but I don't see it fully yet. Let's complete the square on y to determine the nature of this cylinder. Let's complete the square on y. So here the x squared plus the y squared minus 4y. So we say in completing the square, you take the y term, you take its coefficient, it's -4. Take half of it, right? Take half of -4, we get -2. Square it, we get 4. So we're going to add 4 to both sides of the equation. If it's just one side, you add and subtract it. But since we have equal to 0, we're going to add that 4 to both sides of the equation. So this is plus 4 is equal to 0 plus 4. We get 4 over there. We do that, we get x squared plus, this is a perfect square trinomial, y minus 2, all to be squared, is equal to 4. This is a cylinder with radius r equal to 2, center point at 0, 2, z, where z is Z consists of all the real numbers. If it was just a circle, the center would be 0, 2. But since it's a cylinder, then the rulings are with respect to the z-axis. Right? So this guy, it shifts a little bit on the y-axis. Let's see. So the center is not the origin anymore. So here, x is 0, y is 2. It's there. So I get, why is it doing that? Okay. This line, that black line doesn't come out like that. It's just the crippledness of my hand. You know? Fred Sanford called it arthritis, where he couldn't, Lamont said, you need to clean up around here, Pop. He said, my arthritis, son. So, right. Any questions there? Let's see. Look at the next one. Convert the point from rectangular to spherical coordinates. So we've been looking at basically rectangular, cylindrical. Let's look now at some of the points where you have to deal with spherical coordinates. So here, x is equal to -2. Y is 2 times the square root of 3. And then z is equal to 4. So we need, for spherical, we need rho, theta, and phi, phi, pho, we need phi. So to get the rho, we can take the square root of x squared plus y squared plus z squared. So this is the square root of -2 to be squared is 4, plus this is 4 times 3 is 12, plus 16. This is the square root of 32. So rho is equal to, what is that, 4 times the square root of 2. Okay. So that's rho. So now we need theta. We use the tangent. Theta is equal to y over x. Y is 2 times the square root of 3, and x is -2. So here I get the square root of 3 over -1. Since this is involving the square root of 3, then I'm thinking my 30, 60, 90 again. So it's 1, 2, square root of 3, 60 degrees, power over 3, 30 degrees, power over 6. Now look here to see if I can get the reference angle that would relate this tangent theta of the square root of 3 and a 1. So that reference angle here, the tangent would be this of power over 3 would give us square root of 3 over 1. So the reference angle is power over 3. But here, notice that x is negative and y is positive. What's that, the second quadrant? Yeah, so x negative, y positive, second quadrant. So if it's the second quadrant, we say that here theta, the angle, is pi minus pi over 3. Right? So you get 2 pi over 3. Is that what you said? You added pi to pi over 3. Yes, sir. If it's the third quadrant, we'll add pi plus the reference angle. But if it's the second quadrant, it's pi minus the reference angle. So theta is 2 pi over 3. So we got rho, we got theta. So now we need phi. Now to get phi, we said use that cosine of phi. Right? So cosine of phi is z over rho. And the reason why we're using that is because we already have z. Z is 4, and we already have rho. 4 times the square root of 2. So z is 4, and rho is 4 times the square root of 2. This guy is 1 over the square root of 2. Well, you recall that's directly of phi is equal to pi over 4. So for spherical coordinates, it's rho first, then theta, and then phi. So here rho is 4 times the square root of 2. Theta is that 2 pi over 3, and then phi is the pi over 4. Any questions there? Convert this point from spherical to rectangular coordinates. Didn't bring my printout. So if it's spherical, that means that rho is given to be 4. Theta is given here, that middle term, pi over 6. And phi is pi over 4. So you want to find x, you want to find y, you want to find z. Well, x, you remember, has the form rho sine phi cosine theta. And we have all 3 terms, so we can find that directly. So rho is 4 sine of pi over 4 cosine of pi over 6. So here x is equal to 4 times 1 over the square root of 2, and the cosine of pi over 6 is the square root of 3 over 2. So we get 2 square root of 3 all over the square root of 2, or you can write that as, is that 2 square root of 6 all over 2, just the square root of 6. That's x. What about y? Y is rho sine phi sine theta. So rho is 4 sine of pi over 4, and then sine of pi over 6. So y is 4 times 1 over the square root of 2 And the sine of pi over 6 was at 1/2. 2 over the square root of 2. And that's the same thing, it's just the square root of 2. What about z? How do we get z? Z is equal to what? Yes, sir. You got it. Yep, rho times cosine phi. So rho is 4, and then we have cosine of pi over 4. So 4 times 1 over the square root of 2. Looks like that's just 2 times the square root of 2. So x is the square root of 6. Y is the square root of 2. Then z is 2 times the square root of 2. Well, if you think you got it, let me give you one. See how you do. Can't get no easier than that, right? So here, find the equation in spherical coordinates is given to be in rectangular. What's its spherical form? You should find that equation that says y equal to, and everything on the right side were spherical values, right? And then you just replace that y with the 2, and you have it. So did you find that equation? It says y is equal to, what does that say? I think it starts off with the rho first, right? It's rho sine phi, right? Yep. Yes, sir. Yep. So you find that equation. It says that y is equal to rho sine phi, because rho sine phi together, that's r, and then times sine theta. So this is still y is equal to r times sine theta. Here y is equal to 2, so all you need is just 2 is equal to rho sine phi sine theta. You can't leave. We got to have the rho. Yes, sir. Yes, sir. Yes, sir. My granddaddy's, well, my cousin too, second cousin, his name was Tater. When I was a little boy, he used to come stay with us down in the country. I never knew Tater's real name. We just called him Tater. And and he had a little phrase that he would say. He would say, "Let alone, son, let alone. Let alone, son, let alone." So look, once you get that, let alone, son, let alone. You know, man, don't try to add to it. Yeah. Tater didn't have much education, but I tell you what, he was just a good fella. And Lord bless his soul. Hope to see him in heaven one day. He I don't know what happened. They said when I was probably a teenager that I think he moved to stay with some relatives over in Atlanta. He wasn't made for the big city. He was a country fellow, just like all of us down there in South Alabama. And they said a train ran over him and killed him. So, but I look forward to seeing old Taylor in glory one of these days. I don't know. I was a kid when I first knew him. I was about 8, 9, 10 years old, and he looked to be maybe at that time probably in his 30s. I don't know. So then maybe a few years later is when he died. So he was probably late 30s, early 40s. I don't know. But yeah, he was kind of slow, but just a good fella. Yeah. Um, let's see. Find an equation in spherical coordinates. What do you think about that one? Let's see what you can do with that. Should be just one movement of your hand and you should have it. One movement. 2. Because x squared plus y squared plus z squared is equal to what? Rho squared, right? So you just end up with the equation is, that's it. But r is not in spherical coordinates, right? That's the, yeah. Yes, you do get r equal to 4 from here, but this is good for cylindrical. You don't need it for spherical, so you got to convert that. Oh boy, how would you do that? I don't know. You can relate r to 2 values in the spherical coordinate system directly. R is equal to, but x doesn't help us for spherical. Yes, sir. I wouldn't go that far. I just say r is equal to, isn't r equal to rho sine phi? Yeah, that's all you need. Since we have r is equal to rho sine phi, this implies 4 is equal to rho sine phi. And from there, let alone, son, let alone. All right. Now that's a good one. So we'll convert the x squared plus y squared to r squared, right? So let me do that, and then I'll leave the rest to you. R squared is equal to 2z squared. All right, so now you got to figure out how to get rid of r, how to get rid of z, and to have some maybe combination of whether it may be theta, phi, or rho, I don't know. You can take the square root of everything. You can get r equal to the square root of 2 times z. Replace the r with that previous problem that we had, r is equal to rho sine phi. And then you can take that z. Z is equal to something else as well. Yes, sir. Yes, sir. So we can drop this down to r is equal to the square root of 2 times z. And since we have r is equal to rho sine phi and z is equal to rho cosine phi, so we have rho sine phi is equal to the square root of 2 times rho cosine phi. Divide both sides by the rho, divide both sides by that cosine phi. So I have sine phi over cosine phi is equal to the square root of 2. But sine over cosine is just tangent. Tan phi is equal to the square root of 2. Let me skip some of these. There's so many down there, and some of these are very simple. Find an equation here in rectangular coordinates. Here, phi is in spherical coordinates, and then sketch the graph. Find an equation in rectangular coordinates. So we said that if an angle for phi is given, then you want to always wrap that around cosine. Right? If it's phi, so here cosine phi, you recall, is equal to, what is that, z over rho? So cosine of phi, this is cosine of pi over 6, that's equal to z over rho. So the cosine here is the square root of 3 over 2. That's equal to z over rho. If you cross multiply, we get rho times the square root of 3 is equal to 2 times z. I don't want to have the square root anymore, and I do know that rho and z for rectangular are related when they're squared. So I'm going to square everything here. So when I square everything, I get 3 times rho squared is equal to 4 z squared. So this is 3 times x squared plus y squared plus z squared, because that's rho squared, right? And that's equal to 4 z squared. So this is 3x squared plus 3y squared plus 3z squared is equal to 4z squared. So now I'm going to take that and subtract 4z squared on both sides. So I end up with 3x squared plus 3y squared minus z squared is equal to 0. What is that? Huh? We're playing charades. No, there's a 0 there.
Oh, 0. Elliptic cone.
Yes, thank you, elliptic cone. It's an elliptic cone. That's right. With the axis of the ellipse, it's tending with the z-axis, right? This is an elliptic cone. It doesn't pick up the bottom. How come it doesn't pick up the bottom? How come it doesn't pick up the bottom? That's involved, yes. He said the squared nature, we went and took the rho and the z, we squared everything. That's involved, but it comes even before that. What was given initially? What were you given initially? Phi. And phi is defined for spherical coordinates. It's defined where? 0 to pi. You can't go to 2 pi. It doesn't pick up the bottom. Remember we talked about that. The definition for here, for this phi is defined on the interval from 0 to pi only. That's why I can't go all the way around. If you want to get all the way around, then you just take rho and you negate rho, and then you drop down there if you want to. You know what's neat about all this stuff? And I'm telling y'all, man, this stuff will blow your mind. It's going to blow your mind a couple years later when you start dealing with computer coding, which you will, in engineering. And those computer coding will use heavily what we do here in vector analysis. And in those codes, and what I'm familiar with is old stuff, C++ and that type of thing. And it was funny because when I went to grad school in the PhD program, and we were dealing with numerical methods, and I was thinking that we're going to really look at some coding from some different and newer systems. The professors there, they were using Fortran. It was like, man, and this was like in the early 90s, and Fortran was like old then, man. But But look, it works, man. Huh? Fortran. Fortran is a computer code, a computer program. Very similar to, Pascal or BASIC or C++, but a very older system. But what I was fascinated with was whether it was in C++ where you can call up a function, like you have these libraries of functions already there, you can call up a function. All these codes are there. These definitions for these angles are already put in there. And that was the real cool thing, So like everything that we learn in the book, in the math book, is already pre-coded. And whether it's Mathematica, MATLAB, Maple, everything is going to be one-to-one correspondence, what we deal with here in these textbooks with what's going on out there in the computer coding system. That was fascinating to me. I didn't finish it. I was called to a church up in Pennsylvania, and so I left the program to work at a church. I was pastoring a church before I went to grad school, thinking that I could definitely finish up grad school in mathematics, and but the calling was too great, and so yeah. So and since then I've been always working at a church, and so basically what I do here in class is my side job. I just do this for fun, This is neat stuff, man. So yeah. Oh man, I do. You gotta love Donnie, man. All righty. Okay. Let's see. Find an equation in rectangular coordinates and sketch the graph. Let me leave that one for you to do. Let's see if you can do that one right now. Let me give you a hint to help you out. Z is equal to rho cosine phi. I use that in some kind of way with that problem right there. I don't know. You end up with something. I don't know. I usually bring my notes in. I don't have anything, so I don't know what it is. I have to work it out. So I didn't bring anything because once I leave here, I'm going to my car and I'm going to Bob Gibson and get me a half a chicken. Yeah, man. After class. All right. I got some greens and some green beans in my office, so I got enough for you too, Donnie. So, amen. My mom came this weekend. My son graduated from high school, and so mom came from Indianapolis, and she's a big-time cook up in Indianapolis, and so she wanted to come and do a dinner for EJ, and so, man, she laid everything out. And so we're still eating, man. We're still eating, you know. So let's see what you got. Anybody get anything? I think I heard elliptic cone. Anybody else? So here's what I would think. In one way, several ways you can get at it, and either way is fine. But cosine phi, just from what I have here in blue, is equal to z over rho. So I'm going to replace that cosine phi over here with the z over rho. And so here I get rho is equal to 4 times z over rho. Multiply rho by both sides, so I get rho squared is equal to 4z. Yes, sir. Another elliptic cone. So here, this implies that we have the x squared plus y squared plus z squared is equal to 4z. I take that back. It's not an elliptic cone. This is x squared plus y squared plus z squared minus 4z equal to 0. Complete the square on that z. So this is x squared plus y squared plus z squared minus 4z. Take half of the negative 4, we get negative 2. We square that, we get 4. Add 4 to both sides. It's a sphere. X squared plus y squared plus z minus 2 to be squared. That doesn't look so good. It's equal to 2 squared. So this is a sphere with center at 0, 0, 2, and radius is equal to 2. Just a basketball sitting right there on top. Okay.
The center of that
It's,
sphere
it's right
is
here.
at 2 on the z-axis.
Yes, sir. That's right. So it's just a ball sitting right there on the top up there. Yeah, right there on top of the origin. Okay. That's in the same family. Uh, let's see if we can find one that we have not done the type before. I think these two we have not. I don't think we've gone from cylindrical to spherical. I can't do both of them in the time that I have, so I do one of them. Maybe this one. I don't know. It doesn't matter. So let's try this. Convert the point from cylindrical to spherical coordinates. I don't think we went in that direction. Then the other one is going from spherical to cylindrical. So let's try this guy. So R is equal to 6. Theta is equal to power over 2. And then Z is equal to -6. So the good thing going from cylindrical to spherical is that they both use theta. So we got theta already, so that's cool. Um, if they, since they give us R, we know that R squared is X squared plus the Y squared. Then they give us the Z, we can get rho. We know that X squared plus Y squared is the 36, and also Z is equal to -6. So rho squared is equal to X squared plus Y squared plus Z squared. So that gives us 36 plus 36, you get 72. So rho is equal to 6 times the square root of 2, or the square root of 72. So that's rho. We got theta. So now we just need phi, and that's it. What did we say to use to solve for phi? Cosine. Yes, sir. Yep. If you're dealing with theta, you'll look for tangent to get theta. If it's phi, then we always pull up the cosine, because cosine for phi relates rho and z, and you can translate rho to some form of x, y, z, and then z is already in that form. So that's why we want to use the cosine. So we know that cosine of phi is equal to z over rho. We know that z is -6. We just found rho. So cosine of phi is equal to z, -6, all over 6 times the square root of 2. So we get -1 over the square root of 2. So the reference angle is power over 4. And so now we look to see where cosine is negative. What about for cosine negative? What about sine as well? Because for cosine negative, x negative, that could either be in the second or third quadrant, right? But you want to nail that down. So we need to find the value for y, or find the value for the sine of that guy. So what do we do? Just come over here and just we know x is going to be a negative value, but I'm just putting this here, r cosine theta, y is equal to r sine theta. This is 6 times sine of power over 2. That's equal to 6. It's positive.
6 sound power 2 is equal to 6.
Yes, sir, because what's sine of power over 2? 1, right? So that's positive, so that tells me that we're in the second quadrant. Now, I should have known that it's going to be in the second quadrant, not the third quadrant. Why? Well, here, you remember we said that phi is defined from 0 to pi. Yeah. So if I have a question between second or third quadrant for phi, but phi is supposed to be defined from 0 to pi, so it has to be in that second quadrant. So I didn't even have to do all this stuff over here on the side. So if that be the case, phi is equal to pi minus pi over 4. And this is 3 pi over 4. So rho is 6 square root of 2. Theta is pi over 2. And then phi is 3 pi over 4. All right, let's stop right there.